parts are probably the ones at the beginning. So if it were me, tomorrow what I would do is when I come in to take the test, the first thing I would do is I would write down, grab a piece of scratch paper for me, but write down on that piece of scratch paper, once the test is going, the things that you want to remember, the things that you're nervous about forgetting. And so examples, what I said last period, I think 3 good things to write down. Number 1 would be the equation for respiration. So writing out what goes on in respiration. So we've got glucose plus oxygen making carbon dioxide, water, and ATP. That's the first thing I would write down. Second thing I would write down is I would draw a picture of a mitochondria, and then I'd put glycolysis, Krebs cycle, electron transport chain in the right places. And then I would do the same thing with photosynthesis. So I would put thylakoid membrane stroma, and then I'd put where light reaction and where Calvin cycle is going to take place. And so do that first, and then as you go through it, then you can kind of reference that. So if we start then with level 12, basically that's free energy. And so life requires free energy. And so if we were to remove the sun, watch, because this took me at least 2 minutes to make this nice animation. If we were to remove the sun and we were to remove free energy, what would happen to life on our planet? Die. It would, watch it, die. Yeah. Thanks, Ben. So life would be gone, okay? We need an influx of free energy. And if we don't have free energy, then we have death. And so we can store that energy in photosynthesis, and we can release that energy in photosynthesis, or excuse me, in respiration. And so questions I've gotten today are a lot about delta G, or in other words, changing Gibbs free energy. And so to kind of assuage your fears a little bit, if delta G is negative, so if delta G goes down, that's an exergonic reaction. What is the most important exergonic reaction in all of life science? Respiration, okay? So we're releasing energy. It's exergonic. And where's that energy going? It's going to ATP. What's the most important endergonic reaction? Photosynthesis. The delta G is positive, and so we're storing energy. Now that equation is scary to people. And so if you're scared of the equation, think of this. On a free energy diagram, we have more energy to start in glucose and the oxygen than we do at the end, and so the delta G is going to go down. We're going to lose free energy. Where does that energy go? It goes into ATP, and we're going to lose some of that energy as heat. What's the opposite of that? We're storing energy in the glucose. Do you remember this? Where's the energy stored in glucose? Bonds between the carbon and the hydrogen. Okay? And so what you'll find this theme is that we're storing energy in the electrons, and then we're releasing the energy. And it just kind of cycles back and forth like that. And so if we get to what really 12 is about, is it how we go from free energy of the sun to the free energy of the movie. And so this is that equation that I said would be super important to write down first. Either the equation for respiration or the equation for photosynthesis. And so what's going on, we're taking glucose plus oxygen, making carbon dioxide, water, and then we're storing that in ATP. Now I simplified it, right, a little bit. There are coefficients in front. So there's 1 glucose plus 6 oxygen makes 6 carbon dioxide plus 6 water. Yeah, tough.
How important is it to know that exact equation?
I mean, everything's important. Yeah, so you got to know everything. You got to know everything. What do you got to know? Everything. Yeah, okay. Now, why I said is it important to write down this equation? Because it's multifaceted. I can turn the arrow in the other direction, and now I have photosynthesis again. Sun plus carbon dioxide, water makes sugar, and then we're going to give off oxygen as well. And so in this slide, the free energy goes from the sun to the glucose, from the glucose to the ATP, from the ATP to the phosphate, from the phosphate to the movement. Our starbursts are getting smaller and smaller. Why is that? Losing energy is heat, right? We're losing it to disorder. But we're transferring that energy from one thing to another, and we're using it to do work. Now, the most missed question on the summary quiz dealing with this was a question where it said, in life, we're coupling a blank reaction with a blank reaction. Do you kind of remember that question? We're coupling an exergonic reaction with an endergonic reaction. So why do we have to couple an exergonic with an endergonic? And why isn't it vice versa? Because exergonic release energy. So we can couple the release of energy from cellular respiration with the storing of energy, for example, of making ATP. And we can do that over and over and over again. Mary, question?
One thing I no change in temperature.
Right.
Wouldn't that zero it out with the,
No, because if we're, let's look at this one, okay? So let's do respiration. We're losing energy. So how much molecules do we have to start? Well, we have 1 glucose plus 6 oxygen, so we're going to have 7 total molecules to start. What are we going to have at the end? 12. And so we're increasing the entropy of the system. So even though this may not change, we're going to increase the entropy of the system. That's going to make our delta G go down.
so if there's no change in temperature, just put in a 1 instead of 0 there?
Right. Yeah, absolutely. Now, if we go 0 here, Kelvin, 0, what happens? Then everything's a wash. You know what I mean? There's no energy anyway. Yeah, I just tried to tap this. That's not going to do anything. But let's tap this one over here. Okay, so let's go to respiration. So again, first thing I would write down is I would write down a mitochondria, and then I'd put everything in its place. I'd then do that with photosynthesis as well. I'd draw a chloroplast, and I'd put everything in its place. Because on this test, yeah, I have seen this in the past, where people get confused between Kelvin, Krebs cycle, NAD, NADPH. Like, make sure you know what's what. And so this is a mitochondria. Where would this be on a mitochondria? Right here. Cytoplasm, right? What's this inside? Matrix. We've got inner and outer membrane, and then what's this in the middle? Intermembrane space. Yeah. So where does glycolysis take place? Outside in the cytoplasm. Okay. What do we do in that? We take glucose, we break it down into pyruvate. What do we get from that? We get 3 things from that. First, we get ATP. Then we get pyruvate, and then we store energy in the NADH. And so a second ago, everybody got this right. Where's the energy stored in glucose? It's going to be between the carbon and the hydrogen. And so if I strip away the hydrogen and the bond itself, those electrons, that's what I'm handing off to NAD. And so what is NAD carrying? NAD is carrying the electrons, but it's also carrying the proton over to the electron transport chain. What is not labeled here? What goes on where the arrow is? Do you remember?
CO2 comes out.
CO2 comes out. What do we create from pyruvate? Acetyl-CoA. And we make another NAD, and that's kind of not on this diagram. As we go into the Krebs cycle, that acetyl-CoA is going to be broken down fully into carbon dioxide. We make a little bit of ATP. Where's the energy go? To our friends NAD and fat. It's going to the electron transport chain. And then finally, we cash all that in at the end. And so where's the show? The show is going to be way at the end. And so let's kind of get to the show. Glucose, breaking down in the first phase is glycolysis. We make ATP and store the energy as NAD. When we make acetyl-CoA, we make a little more NAD and give off carbon dioxide. And then when we get to the citric acid cycle, we're going to break that acetyl-CoA down fully into carbon dioxide, but the energy goes to the NAD and the fat. And so carbon dioxide does not contain that energy in its bonds. But where is the energy in NAD and fat? Which one has more energy, NAD or fat? NAD, okay? It's got electrons that have higher potential energy. And so where are they going to drop off their electrons? Right here. And what about fat? They have a little bit less energy, so they're going to hand it off a little bit farther down. So what is the power of the electrons doing? As it flows through these proteins, what is the power doing? Anybody? Just say it. Pushing the protons to the outside. Okay, so it's changing those and moving it out. Are you with me that that is now active transport? Good. It's taking energy in to pump the protons out here. Now we got a bunch of protons out here. Where are they going to go? The only place they can go through is ATP synthase. And as they do that, that's where we make the ATP. Now let me block for a second. Let's finish it out. You can't see it now. We've got the electron transport chain over here. What happens at the end? Okay, what happens to the electrons once they move through the electron transport chain? Where are they bound? Where are they headed? They're going to combine with oxygen. So we got electrons, oxygen. What's the third thing that comes together? So we got the electrons, we got the oxygen we breathe in, and the third thing is going to be the protons, okay, that just came through ATP synthase. What do you get when you combine protons, oxygen, and electrons? Water, or H2O. So the H2O is going to be made there at the end. Now, why is that important? Let's look what happened. There was high energy in the electrons of the glucose, and we gradually dropped it down, transferring that energy to NADH and FADH2, and eventually it's all converted to ATP. We've got water now, okay? Thinking ahead to photosynthesis, what's going to happen to the water in the light reaction? Light reaction, what's going to happen to the water? We're going to split it,